Hello guys, this is Prashant from MyLearnCube. So in this lecture, we will see something about Boolean Algebra and we will try to solve some questions that have already been asked in previous year GATE questions. So in Boolean Algebra, we have some variables. We have some variables say A, B, C, and we have some operators just like and, or, and this way, negation. So these kind of operations, and the result of this algebraic function would be either true or false. And in fact, the possible values that these variables can hold are also either true or false. So we will start with some laws. One is AND law. One is AND law. AND law is nothing but if A is any variable, A is any Boolean variable. And what do you mean by Boolean variable? A variable which can have either value true or false. So A and 1 will give you A and A and 0 will give you 0. This is your AND law. These are self-explanatory laws. And OR law is simple. A or 1 is 1 and A and 1 is nothing but your A or 0 is nothing but your A. So these are your AND law and OR law. There is one law called commutative law. There is one law called commutative law. Commutative law says A plus B. This is an example. This can be any operator. A operator B is B plus A. This is your commutative law. Or one more is there, A or B is equal to B and A. Sorry, A and B is equal to B and A. This is your commutative law. So your OR operator, AND operator, all these operators are your commutative operators. This is your commutative law. And one thing is there is a very important law is distributive law. One law is distributive law. These laws are self-explanatory, and if you are preparing for GATE, then you must be well versed with these kinds of operators or laws. So I'm just revising it for you. I will not spend much time on these laws. So what is the distributive law? Distributive law says A, B, then A dot B plus A dot C. One more form is there. A plus B dot C will give you A plus B, A plus C. This is your distributive law. One law is there is associative law. One law is there, associative law. Associative law says A plus, this is your associative law. One more form of associative law is this one. So one operator, that means one question I have seen in previous year GATE question, among these four operators, which A, suppose this is option A, this is option B, this is option C, and this is option D. So among these four operators, which does not bears associative law? So this is your AND operator, this is your OR operator, this is your XOR operator, and this is your nothing but NAND operator. Up arrow is NAND and down arrow is NOR. So this is the answer. How? I will show you. See, if A NAND B NAND C, we will compare it with A NAND B NAND C. Put the value, suppose I will put the value 1 1 0. A is equal to 1, B is equal to 1, C is equal to 0. A is equal to 1, B is equal to 1 and C is equal to 0. Then you will see. Okay. Now as we all know, for NAND gate, this this will come here. In fact, this will come here. Okay. So 1 NAND 1 will give you 0. You must know that 1 NAND 1 will give you 0, NAND 0, and 1 NAND 0 will give you 1 and 1 NAND 1. So this is 0 NAND 0 is, as you know, if there is at least any 0 in your expression, the output will be 1. So it will give you, and if both inputs are 1, the NAND gate will give you 0. So this is not equivalent. Hence NAND gate, NAND operator is not associative. Is not associative. However, there is no need to learn these things. There is no need to mug up these things. You can at instant you can put the values and you can check whether it is or it is not. Okay, good. Now there is something called dual. Dual is something like we have to perform two operators. Interchange 0 and 1. Wherever there is 0, put 1. Wherever there is 1, put 0. And second one is interchange and or operators with each other. Wherever there is and, put or there. Wherever there is or, put and there. So one of the example is, suppose we have this a plus b dot c. So the dual of this operation, the dual of this expression will be a dot b plus c. So this is the dual of this expression. So these all these things are very simple, and I am just revising it for you. No big deal. Now one very important law is there, De Morgan's law. Very important law is De Morgan's law. De Morgan's first law says a plus b to the power bar is a bar dot b bar, and second De Morgan's law says a dot b to the power bar is a bar plus b bar. So these are your De Morgan. You must be aware of that. So these are something these are some very famous laws that you must be encountered through in your syllabus. Okay. Now if I'm going to give you some question. Let's try with some question first. If we have this question, suppose f of a b c and a bar c plus c bar d plus b bar c plus ab, and we want to simplify this expression. So how will we perform? We want to simplify this. So simplification would be like, from this term and this term we can pick c out. So we will have a bar plus b bar in that case, and then we will have c bar d bar this term, and the last term ab. Now this term we can apply inverse De Morgan's law, and we can write this term as a dot b to the power whole bar into c plus ab plus c bar d. Very simple. This is the way. I'm just applying inverse De Morgan's law here. Here I am applying inverse De Morgan's law. Okay. Now from these two expressions we can apply what? Distributive law. When we apply distributive law here, we will get a dot b bar and ab plus c. Distributive law we have already seen, plus c bar d. Then we know that this is, suppose x, this is x bar, and we already know x plus x bar will give you 1. So this term will be nullified. This whole term will be nullified. Cancel out. So we get, from here we get c plus ab plus c bar d. So now we can apply distributive law on these two terms. So we will get c plus c bar, c plus d plus ab. So this will get cancelled out. So the final expression is c plus d a b. So this is the Boolean simplification of this whole expression. Now one can ask why we are performing Boolean simplification at all. The answer is, the Boolean, after doing Boolean simplification, the same expression can be implemented using minimum number of gates. That means the circuit cost will be less. To implement this expression, how many gates we require? 1, this AND gate, plus 1, plus 1. That's only 3 gates are required. But to implement this expression we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 gates. So from 10 gates we have reduced to 3 gates. That's why we required this Boolean simplification, and for this Boolean simplification we have those laws, De Morgan's law, distributive law, and associative law, and all those things. So these laws are useful to get Boolean simplification. Now see one more example. See one more example. We have suppose this one f. We have a Boolean function of 3 variable f a b c bar plus a b bar c plus a b c plus a bar b c, and we want to simplify this thing. If you will start to simplify this thing with conventional approach, it will easily take your 5 to 10 minutes. Easily take your 5 to 10 minutes. So I will here tell you one very nice trick, and the trick is you just identify, I'm writing the trick for you, just identify the term having more common, this is the heart of this trick, more common literals with all other terms, Example, let's see. We have a b c bar, a b bar c, we have a b c, we have a bar b c. So if you keenly observe this term have ab common from here, we have bc common from here, and from this term we have ac common. So this is the answer, ab plus ac plus bc. That's it, done. I think it will take hardly 10 to 20 seconds. What you have to do, just out of these 4 terms, pick the term which has maximum number of common literals with other terms, and those common literals, those common values are collectively forms the answer. This is the one. Let's try with some another question. We have f, a function of a b c, and this is given as a bar b bar c plus a bar b c bar plus a bar b c plus a b c. See this term. This term has bc common with this. This term has a bar b common with this, and this term has a bar c common with this. Hence we get the answer, a bar c plus a bar b plus bc. Done. I think 10 to 20 seconds at the most, and you are done with the answer. This is the way to solve this question. Now one more question we will see. We have f is equal to a dot a plus a c bar plus a b bar c. So this question has been asked in previous year GATE. I don't remember actually what is the year, but it has been asked. So you have to tell that how many NAND gates. The question is how many NAND gates are required to implement this Boolean function. So the simple thing is just start solving this expression. Taking a out of this whole expression, you will get this, and you all know adding 1 to all these terms will give you 1, a dot 1. This a is here, and this whole expression degenerates to 1, and a and 1 is nothing but a. So 0 number of NAND gates required. You have only a. So 0 number of, that means if this is black box, so a is there, b is there, c is there, just put this a outside. So 0 number of NAND gates are required to implement this expression. One more question. Now we have f is equal to a dot b plus b dot c plus c dot a, and we have, then I am asking, f bar would be a bar dot b bar plus b bar dot c bar plus c bar dot a bar. So is it true or false? I would recommend you to just pause the video for 2 minutes and think it by yourself and try to answer this question. Is it true or false? Okay. Now if you think, if you give some time and you are able to figure out this question, now most of you, if you keenly observe, most of you will get the answer false. False. But this is the wrong answer. The answer is true. See how. F we have. F bar would be A. F bar would be means to try to solve this question. But how will you get F bar? That means F bar means bar of this whole term. Bar of this whole term. And bar of this whole term will give you applying De Morgan's law. Now you can see the importance of De Morgan's law. Applying De Morgan's law on this whole equation, you will get A bar plus B bar. Then you will get B bar plus C bar. Then you will get C bar plus A bar. And solving this very keenly, now you will get the answer. See this term. If you will see this term, then this term is actually equivalent to, if you apply reverse distributive law, then this is equivalent B bar plus A bar, B bar plus C bar. This is equivalent to this one, and we have C bar plus A bar. Now next, applying. Now solving these two equations very keenly, you will get B bar dot C bar plus B bar into A bar. From here you will get A bar, C bar, C bar, and from here you will get A bar, C bar. Now this is B bar, C bar, this is B bar, A bar, and these two terms are actually degenerates to A bar, C bar. And if you see, this expression is nothing but equivalent to this expression. Hence the answer is true.